In this video, I'm going to walk through the code needed to take a dataset of points and count how many points are located in different areas. We can use this code to work out things like how many crimes have occurred in different neighborhoods or cities. And as an example, I'm going to count how many carjacking offenses happened in each borough in Mexico City in 2019. The first thing I'll do is load the packages I need. In this case, I need the SF package because we'll be working with spatial data, and I'm going to load the tidyverse package for various functions to help with data wrangling. Next, I'll load the data that I need. Both datasets here are in spatial formats already, which I can tell from both files having the gpkg file extension that's used for geopackage files. Since the datasets are in spatial formats, I can load them with the stread function. Before I go any further, I'll have a quick look at both these datasets to help in writing the rest of the code. I can use the head function to look at the first few rows of each dataset in the R console. I can see this dataset contains one row for each carjacking, and I can also see that it uses the WGS84 coordinate system, which is the most common coordinate system that uses latitude and longitude coordinates. If I do the same with the other dataset, I can see that there is one row for each of the 16 boroughs in Mexico City, with borough names stored in the nom-geo column. This dataset also uses WGS84, which is important because in the next step we need to use two datasets that use the same coordinate system. If the datasets had different coordinate systems, I'd need to transform one of them using the sttransform function. But fortunately, in this case, I don't need to do that, so I can go on to the next step. Now that I've got the data I need, I can use the stjoin function from the SF package to identify which borough each carjacking happened in. The stjoin function combines data from two datasets based on the spatial locations associated with each row in each dataset. In our case, the first dataset contains points representing crime locations, and the second dataset contains polygons representing borough boundaries. stjoin takes the points from the first dataset, lays the polygons from the second dataset over them, and assigns values to the points based on which polygon each point falls within. So you can see that the resulting dataset contains all the data from the first dataset and all the columns from the second dataset. The first two rows of those columns have values that come from the first polygon, since those 2 points both fall inside that polygon. The next two rows of the A and B columns have values that come from the second polygon. The final row has missing values for the two columns that come from the polygons dataset, because the point corresponding to that row falls outside all of the polygons. We're going to use stjoin inside a code pipeline because we need to do a few more things after we join the data. Because we're running each function inside a pipeline and assigning the final results to the carjacking counts object, we usually wouldn't see what the data looked like after each step in the pipeline. But I'm going to show you what the data would look like at each step if we wrote the code so that each function was done separately, rather than inside this pipeline. After we run stjoin, the data contains all the columns that were present in the CDMX carjacking object, as well as two extra columns that have been joined from the CDMX alcaldias object, municip and nom-geo. Once we've joined the points to the polygons, the next thing we need to do is to convert the result of stjoin from an SF object to a regular non-spatial tibble. To do this, we use the stdropGeometry function, which simply removes the geometry column from the data. Now we're doing that because it makes the next function in the pipeline run much faster, since it doesn't have to wrangle the location data stored in the geometry column. If we looked at the data at this point in the pipeline, we'd see that it looked identical to the data in the previous step, but without a column holding the geometry for each row. The next thing we do is count how many rows in the data have each unique value of the nom-geo column, which is the column that contains the borough names. We do this using the count function from the dplyr package, and specify that the column containing the counts of crimes should be called offences. If we were to look at the data at this point in the pipeline, we'd see that we now have a dataset with two columns and one row for each borough. We now have counts of carjacking in each borough, but to plot those counts on a map, we need to join the count data back to the outlines of the boroughs in the CDMX alcaldias dataset. To do that, we use another type of joining function called leftjoin. Whereas we used stjoin to join datasets based on the spatial locations of each row, we use leftjoin to join two data sets based on finding matching values in one or more columns in the data. Imagine we had two data sets called left hand and right hand. The left hand object has two columns, x and y. The right hand object also has two columns, but called x and z. We can join these two data sets using the left join function, which takes the left hand data set and adds to it values from the right hand data set. The important thing to remember here is that values from the right hand data set are only added to the data from the left hand for rows that have matching values of the column we specify in the by argument of left join. In this example, left join will take all the data from the left hand object and add new columns to store the values from the right hand object. It then fills in those new columns by looking for values in the x column in the right hand object that match the values in the x column in the left hand object. In this case, there are matching values for x equals a and x equals b, but no matching value for x equals c, because there are no rows in the right hand object that have a value of c in column x. In that case, the value of the z column in the combined data set will be NA to mark a missing value. You might also have noticed that the final row in the right hand data set is not present in the combined object at all, because the combined object only contains values from right hand that match values from left hand. That is why the joining function is called left join, because it keeps all the values from the left hand object. Because left join only keeps matching rows from one dataset, it's very important that we carefully choose which order to provide datasets to left join. In this case, we want to produce a dataset of counts for all the boroughs in Mexico City, so we'll use the object containing the borough boundaries as the left-hand dataset that we provide to left join. This is important because if there are any boroughs that had no carjackings in 2019, those boroughs would not be listed in the carjacking counts object. That means if we used carjacking counts as the left-hand dataset, some boroughs might be missing from the final object. The column name that is present in both datasets is the nom-geo column that holds the names of the boroughs. So we choose that as the value of the by argument. The final thing we need to do is replace any missing values in the offences column in the combined dataset. As I've already talked about, if there are any rows in the left-hand dataset that don't match any rows in the right-hand dataset, those rows will have missing values in the object produced by left join. In this case, those missing values have a very specific meaning. They represent areas in the data that contain 0 points. They're boroughs that didn't have any carjackings. Because we know exactly what these missing values represent, we can replace them with the number 0 to make it clear that 0 offences occurred in that area rather than, for example, that some mistake in our code produced those missing values. We can replace missing values with the replace NA function from the tidyr package. We can use this function in several different ways, but in this case we just want to replace any NA values in the offences column with the value of 0. So we now have the final dataset of boroughs with the counts of carjackings in each one. And just to check what that dataset looks like, we can quickly create a map with ggplot. We've now got the final code we need to count the number of crimes in different areas, or to count points in polygons more generally.